So we've looked at some techniques for solving linear equations. Now we're going to look at some applications of those. Some big ideas for us to keep in mind as we look at these applications. We'll see that word problems can translate real situations into equations that we can then apply our techniques to solving. While later in the semester or later in the course, we'll examine ways to use multiple variables. We'll see that using one variable is often enough to solve these equations. And we'll also see that the kind of equation that we have to use depends on the context, and we'll come across some formulas that can be particularly useful in solving these application problems. We'll see as we go through these that there isn't a one-size-fits-all way to approach these problems, so instead we need to develop a more general problem-solving strategy. That's going to include defining our variables very clearly, drawing a picture when we can, figuring out an equation that we can base on the situation. Sometimes we have to write multiple equations. Once that's done, things get a little more comfortable because here we can then solve the equation and interpret the results. And lastly, what we're going to see for any word problem that we approach is that we want to check that our solution makes sense in the context of the problem. Let's start with a fairly typical kind of example of this, a mixture problem. So in this example, we have a solution that we're going to make, and we're going to make it by mixing pure water with a 30% acid solution. We want to end up with 10 liters, that's 18% acid. So in other words, the water is going to dilute the 30% acid solution down to 18%. So we want to figure out how much water do we need and how much of the 30% solution do we need in order to do this. So here we can actually think about a picture. We can imagine we have a container here. This contains our water. This is 100% water or 0% acid. Let's think of this as 0% acid. And then we're going to mix with that our solution, our first solution. This is, let me actually move this. Right, this is 0% acid. And this one is 30% acid. And what we're going to do is imagine pouring these two containers into some other container that's maybe bigger. And this is our mixture. And that mixture has to be 18% acid. Okay, so with this picture in mind, we're going to let's let X be the amount of water we need. So we've defined a variable here. We then know, since we ultimately need this container contains 10 liters, if this contains X liters, the second container must contain 10 minus X liters, so that they add up to 10 ultimately. The other thing we want to think about is how much acid is in these. So the X and 10 minus X represent the amount of liquid in each container, but we want to think about the amount of acid. Well, since the water is 0% acid, this contains 0 liters of acid. This one's 30% acid, so we could imagine filling this up to about 30%. That's the acid that we have in that container. Well, we represent that, since it's 30%, we write it as a decimal, and we know there's 10 minus X liters of liquid in there, so that means we have 0.3 or 30% times 10 minus X liters of acid in this container. Over here, we have 10 liters, and that's 18% acid. So if we take 18% of 10, so first of all, 18%, maybe it looks like this. So here's our acid down here, 18%. 18% is 0.18 times 10, which means we have 1.8 liters of acid in this container. So now we have now we have an equation that we can combine. We know that 0 liters of acid plus, in other words, the acid in container 1 plus the acid in container 2, which is 0.30 times 10 minus X. Those have to combine, that's container 2. When we add container 1 and 2, they have to equal the amount of acid in the third container, which is 1.8 liters of acid. So we know two things, that the amount of liquid in the two containers has to add up to 10, and that the amount of acid in the first two containers has to equal the amount of acid in the last container, which gives us our equation. We can now solve this. So 0.3 times 10 is 3. We get minus 0.3x equals 1.8. We use our techniques for solving, so I'm going to subtract 3 from both sides. I get negative 0.3x equals 1.8 minus 3, which is negative 1.2. I'm going to divide both sides by negative 0.3. And I get that x is equal to 4. Now we have to answer the question, which is how much of each do we need? Well, x was the amount of water, so we need 4 liters of water. And then we needed 10 minus x, so 6 liters of our 30% solution. If we want to do a quick check, we can note that 30% of 6 is 1.8, 0% of 4 is 0, and so we do in fact have the 1.8 liters of acid that we knew we were going to need. Let's try another mixture problem. This time, instead of having solutions, we're going to mix coffee, and the coffees are worth different amounts. So we have coffee worth $12 per kilogram, and we're going to mix that with some other cheaper coffee for $8 per kilogram. We want to end up with 20 kilograms of coffee, which is worth $10 per kilogram. And so we want to know how much of each kind of coffee we should use. So we can again think about a picture for this. We have our first bucket of coffee. This is our $12 coffee. All right, it's coffee 1, and we're going to add that to coffee 2. This is our $8 coffee, and we're going to end up with some 20 pounds or 20 kilograms at $10 per kilogram. All right, so we need a variable here. Let's let x be the amount of coffee at $12 per kilogram. So x is the amount of coffee at $12 per kilogram. Well, since we need 20 kilograms total, that means that this must be 20 minus x, so that we have 20 kilograms over here. Now, given that variable, we can figure out how much each of these bins of coffee costs. There's x kilograms in this first bin, and it costs $12 per kilogram. So the cost here is 12 times x. Similarly, the cost for the second bin is 8 times 20 minus x. The cost for the last bin, it's 20 kilograms at 10 pounds. That's $200. The costs should add up. So the cost of the two bins on the left should be equal to the cost of the bin on the right. Well, now we have a linear equation. We can solve this. So if we do that, we get 12x, 160, minus 8x when we distribute the 8, equals 200. Combining like terms, we have 12x and negative 8x, so we get 4x plus 160 equals 200. Subtract 160 from both sides. We get x is equal to 40. That is incorrect. We get 4x is equal to 40, so that we get that x is 10. So we see here that we need 10 pounds or 10 kilograms of our $12 coffee. Ran out of space there. And we then also need 10 kilograms of our $8 coffee. Okay, mixture problems are not the only ones that we can solve using these techniques. We can also solve interest problems. Here we have an investment that's earning simple interest. So the formula for simple interest, this is one where we can't really draw a picture, but we do need a formula. The formula for simple interest is that the interest you earn on an investment is going to be P times R times T, where P is the principal, the amount you invest. R is the interest rate, We're going to use that as a decimal. And T is the amount of time that you invested in. And that's typically in years because our interest rate is typically for some number of years. So we have a total interest of $450 after 3 years at 5%. So we can see here that we're given the interest, we're given the time, and we're given the rate. And we're asked to find the original principal, so we're asked to find P. So if we use our formula, I equals PRT, P is our unknown, that's our variable. We can fill in all the rest of the amounts. 450 equals P times R. We're going to express 5% as a decimal, so that's 0.05, and T is 3. So we get that 450 is equal to P times 0.15. We'll divide both sides by 0.15. And when we do that, you get that P is $3,000. And we can check that. If we take 5% of $3,000, that is 0.05 times 3,000, and that is $150. And that's each year. And we're doing that for 3 years. So timesing that by 3 does in fact give us $450 in interest. All right, we're going to use ideas around simple interest again, but this time we're going to look at a problem set up a little bit differently. So here we have one account earning 6% simple interest and a second account that earns 4% simple interest. We're going to invest a total of $6,000, and we can see that we earn $288 in interest. We'll go ahead and assume that that's for 1 year, and we want to know how much is invested in each account. So I'm going to let X be, I don't have to use X, I can use whatever letter I want, but I'm going to let X represent the amount invested at 6%. If we do that, then 0.06X represents the amount of interest on that account. If we invest X dollars at 6% and we're investing a total of $6,000, then 6,000 minus X has to be the amount invested at 4%. So that 0.04 times 6,000 minus X is going to be the interest at 4%. Well, the two amounts of interest, the 0.06X plus the 0.04 times 6,000 minus X, that has to be our total amount of interest after 1 year. So now we have a linear equation. We can go ahead and solve it. We'll distribute, so we get 0.06X. 0.04 times 6,000 is 240 minus 0.04X. That equals 288. I'm going to combine my like terms, so I get 0.02X equals 288 minus 240, bringing the 240 over, so I have 0.02X is equal to 48. Divide both sides by 0.02, and I get that X is $2,400. So our final answer here is that we have $2,400 invested at 6%, $6,000 altogether, which leaves $3,600 invested at 4%. All right, another common type of problem is a distance, rate, time problem. So here we have an example of that. We have a car that is going for some part of its trip at 60 miles per hour and another part of its trip for 50 miles per hour. We know that the car travels for 5 hours and also covers 280 miles. So we're going to try to figure out how long did it travel at 60 miles per hour. So here we need another formula. We need to know that distance is equal to the rate times time, right? And you use this all the time, maybe without realizing it. If you say, well, I drove for 3 hours at 60 miles per hour, you know you went 180 miles because you're multiplying the two together. So if we think about the car's journey here, we know that this length here, this represents the distance this has a distance of 280. And it also has a time of 5 hours. So there's two different ways to measure the length of this journey. We're going to split it up into two pieces here, where the purple part will represent the distance at 60 miles per hour. And this part will represent the distance at 50 miles per hour. Now, I made one of them longer than the other. I don't really know if that's going to be accurate. When we get to the end, we'll see. Okay, so we know that this distance for the purple part here, this distance here is going to be its rate, 60. So we'll call this distance 1. Distance 1 is going to be 60 times time 1, where D1 and T1 represent the part at 60 miles per hour. And then over here, we're going to have the second distance, distance 2, which is going to be 50 times T2. All right, well, we have too many variables floating around in here. So let's think about the fact that if T1 represents time at 60 miles per hour, then our other time, T2, has to be 60 minus T1, not 60. 5 minus T1 is our time at 50 miles per hour because the two times add up to 5 hours. So what does that tell us? Well, then that tells us our two distances are this distance, the purple distance plus the pink distance have to add up to 280. So we have 60 times T1. That's our first distance. Then our second distance is 50 times 5 minus T1. That's our second distance. Those two add up to the total distance, which is 280. And now we have a linear equation with one variable in it, so we can solve that. We have 60 T1 plus 250 minus 50 T1 equals 280. That's going to give us 10 T1 is equal to 30, so that T1 is 3. And remember, that's the time, so that's going to be measured in hours. And T1 was, in fact, the time at 60, so the car went 60 miles per hour for 3 hours. All right, one last one. We're going to look at, again, a distance, rate, time. So we'll be using the same formula, distance equals rate times time. But this time we have two cyclists who start at the same point. So here's their starting point. One's going to ride east at 12 miles per hour. The other is going to ride west. I'm going to use a different color for that one so you can see the difference, at 10 miles per hour. At the end, they are 88 miles apart. And we want to figure out how long did they ride for. So we know that the distance that the rider on the left traveled, their distance, is going to equal their 10 miles per hour times however long the ride was. So now I have not done a good job here of defining my variable. So I'm going to let T represent the length of the ride. Now, because they're starting and ending at the same point, both of them are riding for the same amount of time. So when I say length of ride, I mean in, let's say, hours. They're both riding for the same number of hours. They're just going to achieve different distances because of their varying rates. So over here, our distance is going to be 12 times our time. So we have two distances, 10 times time plus 12 times time, and they have to add up to 88 miles. So we have to get this equation that 10 times t plus 12 times t equals 88, right? This is the distance for rider 1. This is the distance for rider 2. They end up 88 miles apart, so the addition of those has to equal 88. So we get that 22t. This is a very easy linear equation to solve. So t is equal to 4. So the ride was 4 hours long. We can do a quick mental check. That means that this rider over here, this rider went 48 miles. And this rider went 40 miles, and those do in fact add up to the 88 miles that were covered between the two of them. All right, so wrapping up what we've seen here, we know that applications are going to rely on careful translation into equations. This is often the most difficult step in one of these, is setting them up properly. We've seen that we can solve a lot of these real-world problems by using just one variable. In the future, we'll look at ways to use multiple variables. But for now, we're focusing on solving ones where we can rewrite everything in terms of only one variable. And we also saw that there are some key formulas, that distance equals rate times time, knowing how to accurately use percents, and also the simple interest equals principal times rate times time formulas were helpful to us throughout these.